So here we are for today's lecture, referencing once again our course outline, where check marks indicate topics that we've just completed recently, and arrows represent topics that we'll be discussing today. So here we are in the second unit of our course. We had previously established the building blocks. We're now trying to understand their behaviors. We found quite a lot about the interaction among our particles, namely electricity and magnetism, and we learned that its effects arrive in these discrete packets, which we call photons. The arrival of these packets, though, appears to be random, as in the G.I. Taylor experiment, but at least they occur according to a probability distribution that we can calculate and which corresponds precisely to the brightness patterns that we would calculate using our normal light or wave type physics. What we learned especially about the photons, though, was that when they deliver their little energy packets, they come in a fixed size, which depends on the frequency, and also they deliver a fixed amount of momentum, which again depends upon the frequency of the light. For the electrons, this is where we were discussing most recently, we learned that they too appear to arrive randomly. They produce exactly the same type of patterns that we see with the photons. We saw that beautifully in G.P. Thomson's experiment. And what we learned was for these electrons, they again seem to follow exactly the same brightness patterns that we can calculate with the same mathematics. But now we need to know a wavelength associated with those waves, and we have very strong evidence that it is simply Planck's constant divided by the incoming momentum of the particles. Now, if we want to continue and building on this idea and want to understand in particularly how things change in time, we will need to know not only the wavelength of the particles, which is something we described last time, but now today we will be discovering what the frequency we need to associate with these particles has to be in order for us to be able to, for example, reproduce particle trajectories. So that's the other topic we'll be talking about. To what extent can we reproduce classical particle trajectories? This is something that we need to know will work if we want the correspondence principle to be able to explain not only these new microscopic experiments, but also all of the well-known macroscopic classical Newtonian physics. Finally, for our building blocks, you recall we have our interaction and our two basic constituents of matter, electrons and nuclei. And for the nuclei, all I want to do really is just make a short comment right now today. And that comment is simply that the nuclei, which are act, just like more or less like particles, just like the electrons, it's not too surprising then that because these are like the electrons particles as opposed to representing some kind of an interaction, the nuclei actually ends up behave just like the electrons. We just don't have time to go into all the experimental evidence for this, but there's a whole parallel set of very beautiful experiments done with nuclei and atoms reproducing the same types of behaviors that we've seen with the electrons. So my comment on the nuclei is that they actually also obey lambda equals h over p, right? And they will obey the same thing just like electrons for the frequency. The only difference really is that the nuclei have different masses and charges, and those masses tend to be much larger than the mass of the electron. But aside from that, their behaviors will be exactly parallel to the electrons. So with that comment made, let's then proceed with today's lecture. We want to see if we can discover just what frequencies we need, and the way we're going to do that is to try to build a wave packet that can follow along the classical particle trajectory. Now, as we are building up that theory, what I want you to notice is we're kind of in a transition right now between understanding the basic behavior of the building blocks and building up a theoretical point of view. But I want to point out that our first pass at building a theory from all this experimental evidence is going to be mostly qualitative in nature, or we could say semi-quantitative in nature. We won't build a completely formal theory yet. I want us to get a very strong feel for the implications of all these ideas that we are discovering before we go on to that. But we're kind of making that transition now because we're going to analyze whether or not we can make a wave packet here for our electrons.